We'll move to the next session on ray optics now. We'll be starting with the refraction. Reflection is no more there in syllabus, so we'll start with the refraction. I'll give you the equations required and then we'll go to the question paper, okay? So, we'll start with the concept of refraction. What is refraction? Whenever a ray of light goes from one medium to another, it undergoes a bending at the boundary, okay? Look at this. This is air-water interface. Air-water interface, okay? And a ray of light is going from air to water, right? This is called the incident ray. And there is a normal which you can draw here. Normal is perpendicular to the surface and the ray undergoes a bending here, right? The ray bends towards the normal or away from the normal depending upon the types of media you have, okay? So let me repeat that. We have a pair of media, air and water, and a ray of light is coming from air, coming through air, it is falling on the surface. What happens now? As the ray of light enters the second medium, it undergoes a bending at the boundary. And this bending is known as refraction. Refraction. Okay. So actually, you expected the ray to go along this path. Instead, the ray has come closer to the normal. This is known as incident ray. This is called the normal, and this is called refracted ray. Okay, this is called angle of incidence and this one is angle of refraction. Angle of incidence and angle of refraction. And what is the reason for this refraction of light? Refraction of light happens because of difference in velocity of light. Difference in velocity of light in different media. Light travels with the different velocities in different media. This is the basic reason for light to undergo refraction, the phenomenon of refraction. Okay, that is point number one. Point number two, upon refraction, there is only one thing that remains unchanged. Frequency remains unchanged during refraction. So if the incoming frequency is new, the frequency in the second case is also new. Okay, so let me repeat this. What causes refraction? Velocity of light is different in different media. It is the least in vacuum. It is the greatest in vacuum. It is 3 into 10 power 8 meter per second. While in diamond, it is much lesser, right? Different media, in different media, light's velocity is different. Okay. Anyway, this difference in velocity is causing the phenomenon of refraction. So what is refraction in the first place? Bending of light at the boundary. And this is causing some visible phenomena like twinkling of stars. Twinkling of stars. Twinkling of stars is due to what? That is due to refraction. I told you, right? During the discussions, twinkling of stars appear to twinkle, and this happens because of refraction. And setting sun can be seen again if you stand up on a beach. Just imagine you're lying on a beach and you see the sun setting, and if you stand up, you can see the sun again. This happens because of what? Refraction. I told you the reason for this. And you know, you may have a question here. What is the principle of physics associated with this? They might ask. Okay, so refraction causes twinkling of stars. Stars appear to twinkle, and that's because of what? Refraction. Because there is a variable refractive index for atmosphere, and that keeps changing, and this gives an impression that there is twinkling of stars. And then what? Setting sun. You know, if you watch the setting sun on a beach, if you're lying on the beach, if you stand up, you can see the sun again. And this is happening because of the refraction. Or if you keep a pen in a beaker, if you fill it with water, at the boundary, the scale appears to be bent, the pen appears to be bent. That is also happening because of refraction. So these are actually visible phenomena that happen because of refraction. Okay, now next point is, like I told you, this is incident ray, this is refracted ray, this is normal. All right, angle of incidence, angle of refraction. What are laws of refraction? The incident ray, the refracted ray, and the normal are in the same plane. So next point we have to know is laws of refraction. Laws of refraction. So what are laws of refraction? First law, it is similar to that we learned in class 10. We had laws of reflection. So law of refraction is what? The incident ray, refracted ray, and the normal are in the same plane. That means they are all on the ball. If incident ray comes grazing the surface, refracted ray won't come out of this. That would still stay on the surface. So incident ray is on the board, normal is also on the board, even the refracted ray is also on the board. on the board. Okay. And next point is normal ray. For a normal ray, no bending at all. No bending at all. Normal ray. No, just imagine you have a surface here and a ray of light is falling normally. Look at this. This is normal incidence. For normal incidence, the ray won't bend to either direction. The ray will go straight. The ray won't have refraction. Okay. The ray won't bend. And next point is second law of refraction. The ratio of sine or the angle of incidence to sine or the angle of refraction is a constant for a given pair of media. This is called relative refractive index. So for a normal ray, there is no bending. Like I told you, frequency remains unchanged. Frequency is the only characteristic that remains unchanged during refraction. It's always fine, no issues. Right. And then law of refraction, according to second law of refraction, which is also called Snell's law, sin I by sin R is equal to n2 or n2 divided by n1. What is this? How is this read? Refractive index of second medium with respect to first. That is called relative refractive index. And that is actually n2 by n1, where n1 and n2 are absolute refractive indices of the two media. Okay, so this is Snell's law. And whenever you are, okay, right, that is one point. And then we have one more point. What is a denser medium? What is rarer medium? You know this. Whenever a ray of light goes from a rarer to a denser medium, it bends towards a normal. This is a rarer medium. This one is denser medium. How should you say? I'm talking about optical density here, not normal density. Normal density has got nothing to do with optical density. Okay, for example, you take pure water and then add some impurity, you are changing the optical density. Okay, the color gradation, when it changes, obviously optical density changes. So optical density is more related to velocity of light. So if the medium is optically denser, that means velocity of light is lesser inside. Okay, optical density is a measure of velocity of light. Rarer to denser towards a normal, denser to rarer away from the normal. Whenever a ray of light goes from a rarer to denser medium, it bends towards the normal. If it goes from a denser to rarer medium, it bends away from the normal. And then there are four media you have to learn by heart. First one is water. Refractive index of water is 4/3, which is 1.33. Refractive index of glass is 3/2, that is 1.5. Refractive index of diamond is 12/5, that is equal to 2.4. So that is all about the first part. I'm repeating the whole thing one more time very quickly. Right. So what is the first point we have? Refraction. What is refraction? Bending of light at a boundary. Whenever a ray of light travels from one medium to another, it undergoes a bending at the boundary. And this is called refraction. And what causes refraction? Different velocity. Light has different velocities in different media. Light has greatest velocity in vacuum, and velocity is much lesser in diamond. Light has different velocities in different media, and this is actually causing the phenomenon of refraction. And then frequency, it's an important point. This is a very important point. We can have a one mark question there. Frequency is the characteristic that remains unchanged during refraction. The incident ray, refracted ray, both will have same frequency, but wavelength will change. Consequently, velocity also changes, keeping the frequency same. Then, refraction causes different phenomena, such as twinkling of stars. That actually happens because of what? Refraction. The air has variable refractive index, keeps changing. And then if you watch the sun setting, if you stand up on a beach, you can see the sun setting again. This is happening because of what? Again, refraction. Okay, or if you keep a scale dipped in water, at the boundary, the scale appears to be bent. And that's also happening because of refraction. So there are many practical applications for or illustrations for refraction. Okay, and then for a normal ray, if a ray is falling normally, it won't undergo bending, it will go straight like this. It won't have refraction. And then what? There are two laws of refraction. First one is incident ray, refracted ray, and the normal are in the same plane. That means if you draw one of the rays on the board, the other two are also to be drawn on the board. Okay, they are to be in the same plane. And then second one is called Snell's law. The ratio of sine of the angle of incidence to sine of the angle of refraction is a constant for a given pair of media. And this constant is called n to 1. How do you read this? Relative refractive index. Relative refractive index. Refractive index of second medium with respect to first. Refractive index of second medium with respect to first. It's called relative refractive index. Both the media involved will be non-air media. But this is called absolute refractive index. One of the media involved is all the time air. Okay, refractive index of second medium by refractive index of first medium. Right. And then rarer, denser optical density. Optical density is a measure of velocity of light. Greater the optical density, lesser is velocity. Okay. A medium is said to be denser if velocity of light is lesser inside, and rarer if velocity of light is more. Okay, rarer to denser towards the normal. If a ray is entering from a rarer medium to a denser medium like air to water, it is bending towards the normal. Denser to rare, it is bending away from the normal. Right. Then we have refractive indices of water, which is 4 by 3, 1.33. Then glass 3 by 2, 1.5. Diamond, it is 12 by 5, that is 2.4. And remember, optical density has got nothing to do with the normal density. Optical density and normal density are in no way related at all. Okay. And this is the basic idea of refraction. Did you understand all these things? All right, we have seen Snell's law. And how do you apply Snell's law? Never ever forget this. While applying Snell's law, you should write, sometimes it can be sin R by sin I. It doesn't need to be sin I by sin R all the time. Depending upon conditions, it can even be sin R by sin I. So how do you write this? You should write sin by sin is equal to refractive index. Then the angle inside the denser medium should come on denominator. Angle inside rarer medium should come on numerator. Angle inside denser medium should come on denominator. You can write this down if you want. So you can write as we do on board, okay? As I do on board. So whenever you apply Snell's law, never apply in its regular form. Instead, you just take it this way, n is equal to, otherwise you'll definitely go wrong, n is equal to sin by sin. Then angle inside the denser medium should be written on denominator. Angle inside the rarer medium should be written on numerator. So inside on denominator it has to be angle in denser medium, and on numerator it has to be angle inside rarer medium. Hope you have noted this down. Okay, and then I'll write few equations now. Look at this. First equation is refractive index. What is the equation for refractive index? Velocity of light in vacuum by velocity of light in medium. This is something you've been seeing since class 10. Velocity of light in vacuum by velocity of light in medium. It is a unitless dimensionless value. This is a unitless dimensionless constant. A refractive index. And this could be written as nu into lambda air by nu into lambda m. Why? Because nu is equal to c by lambda. Hope you remember. So cross multiply. C will be nu lambda. C is equal to nu lambda. Nu lambda air by nu lambda m. Why do I write nu here on both denominator and numerator? Because frequency remains unchanged during refraction. I told you in the beginning, right? Let me repeat. The C may be written as, just give me a minute. Okay, so the C may be written as what? C may be written as nu into lambda, and then on denominator it is nu into lambda again. But nu's are the same, be it in a medium or in the first medium. It has to be the same. I told you frequency never changes upon refraction. So that gets cut here. Leaving you with an equation. N is equal to lambda air by lambda m. This is a very, very important equation which we use even in wave optics. This equation is very important. Now, second equation is, when you think about refractive index, relative refractive index, N21, how do we write this? N2 divided by N1, which is actually C by V2 by C by V1. Am I correct? Because N is equal to C by V, so N2 is equal to C by V2 by C by V1. And then C and C are cut. This goes to numerator. V1 divided by V2. And this is what? Nu into lambda 1 by nu into lambda 2. Nu's are cut. You're getting what? Lambda 1 by lambda 2. This is N21. That is another equation. But that's an extreme level question. Very rare chance of this question being asked. And during our regular discussion class, I have done this equation. Okay, the first equation is important. I've seen that in previous papers. Okay, N is equal to C by V. That is N is equal to lambda A divided by lambda M. But in a medium, if a second medium is also involved, you got to look at relative refractive index. What is relative refractive index? N21, which is N2 over N1. That is C by V2 by C by V1. C and C are cut. V1 goes numerator. V1 by V2. That makes it what? Nu and nu are cut. Lambda 1 divided by lambda 2. So N21 is equal to lambda 1 by lambda 2. This is the second equation you have. Did you understand this? All right. So next point is, you won't have numericals based on this, but anyway, just know this. If we have a slab like this, glass slab, and if a ray of light is falling on the first surface, it undergoes a bending, it falls on the second surface, it goes out like this. And if you draw this incident ray, extend this incident ray, and if you consider this emergent ray, you can see that they are parallel to each other. We have proved this in class. Okay, that proof is an important question. It's there in the textbook. Show that the incident ray and the emergent ray are parallel to each other. Just write it down if you want. So in that case, you will show that angle of incidence is equal to angle of emergence. So just in case you have a question, like this. So just note this down. The proof I'm not discussing now. I don't have time. Anyway, just know that if a ray of light is falling on a surface, transparent surface, it undergoes two bendings before emerging. It is entering from air to glass here, air to glass. So it bends to the base, bends to the normal. Then upon falling on the second surface, it is bending for one more time. But this time around, it is going from a denser medium to a rarer medium. Look at this. It is entering from air to glass. Here it is going from glass to air. Right. First one is from air to glass, rarer to denser. Second one is from denser to rarer. But anyway, as you can see, these rays are parallel. These rays. Which rays? The incident ray when extended and the emergent ray. They appear to be parallel. Which makes what? This angle and this angle equal. Angle of incidence is equal to angle of emergence. Just note this down somewhere. Angle of incidence is equal to angle of emergence. That is point number one. Point number two, this is another important area where you can have questions, numericals. Okay. So I won't discuss the derivation. I have a beaker here and it is filled with water, and I'm keeping a coin over here. The coin is viewed from different angles. One straight up. I'm looking from here. Now my eye is located here. That is normal viewing. And I can have oblique viewing. I can look from this side. So if I extend this, if I extrapolate this, it will touch here. That means the image appears to be located here. The image appears to be slightly shifted upwards. Okay. There can be two questions here. What is the equation for refractive index here? Real depth divided by apparent depth. Apparent depth means the depth that you're feeling. Apparent depth, right? So real depth divided by apparent depth. Real depth is this. This is real depth. Okay. And this depth is apparent depth. Apparent depth. They might even ask you to find the shift in the position. How much of shift is there for the image? So I'll put it one more. I'll tell you one more time. You take a beaker and then put a coin inside and then fill it with water and view this coin by at two different angles. One normal viewing, second one is oblique viewing. When you view normally, straight from above, the coin appears to be located at its actual position. But when you view at an angle, the coin appears to be slightly shifted upwards like this. Because when you extrapolate this ray, it touches over here, and that is where the image appears to be located. Okay, so I have the real depth of the coin. Real depth means thickness of water. And apparent depth here, the position where the coin appears to be located. And real depth divided by apparent depth will give me the refractive index. So refractive index is real depth over apparent depth. And then what is the shift in the position? As you can see, the shift in the position is this. The coin was originally here. The coin is currently here. Not the coin, the image is currently here. So the shift in the position is this much of distance. It is what? It is actually real depth minus apparent depth. And you can modify that equation to get apparent depth, thickness of the slab into 1 minus 1 by n. You can modify this, but the derivation is not required. You may have a question based on this. We have done this question in class. Thickness, shift in the position. How much of shift is there? The previous question is, you focus a microscope on an ink mark and then you place a glass slab on top of it. See, you put an ink mark on a paper, and then you view the ink mark through a microscope. You focus the microscope on the ink mark. All right. And then you put a glass slab on top of it, glass slab. What happens? The ink mark appears, shifts upward, right? So you have to push the, what you call collimator setup, I mean microscope upward, so as to view the ink mark again. Understood? So they will be asking how much of shift should be there for the microscope, same as the shift in the position of ink mark. I'll repeat the question. You view an ink mark on a paper and then you put a glass slab on top of it. Automatically the image appears to be shifted upwards. How much of shift is there? Same amount of shift should be there for the microscope also. So they'll be asking, like, how much of displacement should be given to the microscope so as to view the ink mark again. So in a way, they are asking you to find the shift in the position. X is equal to T into 1 minus 1 by N. T is thickness of the slab, or here it is thickness of water. Did you understand? So that sums up the first section, and we have one more point here on critical angle. I'll tell you what. We have a medium here. This is a denser medium and this is a rarer medium. Okay, this one is a denser medium, this one is a rarer medium, and we have a bulb or something here from which light rays falling at the boundary. It actually is going from a denser to a rarer medium, so it has to bend away from the normal. I'm looking at a second ray which is falling at an even greater angle, so angle of refraction is also more. If I take a third ray that is falling at further greater angle, so the ray grazes the surface, and if a ray of light falls at an even greater angle, instead of going out, the ray comes back to the same medium, obeying the laws of reflection, and this phenomenon is known as total internal reflection. Repeating, we have a denser medium and rarer medium, and the ray of light is going from denser medium to rarer medium. We are looking at 4 rays which are going from denser medium to a rarer medium. Just imagine this is water. It's water and there is a light bulb here. Okay, this is a light bulb, and light is coming out of it. One ray is hitting the surface. It is going from denser to rarer, so it is bending away. When the angle of incidence increases, look at this, angle of incidence increases, angle of refraction also increases. Angle of incidence further increases, angle of refraction becomes 90 degree. And this angle is called critical angle. So what is critical angle? It is angle inside the denser medium for which the angle of refraction is 90 degree. So what is critical angle? It is the angle of incidence in a denser medium for which the angle of refraction is 90 degree. What if the ray of light is falling at an even greater angle, something greater than critical angle? Instead of going out, the ray undergoes a reflection. Ray is trying to come back, obeying the laws of reflection. Okay, angle of incidence equal to angle of reflection. Forget about it, that part is not required for us. Okay, anyway, this is critical angle, and if it goes beyond critical angle, the ray suffers total internal reflection. There can be different questions here. Question number 1, what are the conditions for TIR to occur? Total internal reflection can be called TIR. Short form is TIR. What are the conditions for TIR to occur? Number 1, the ray should go from a denser medium to a rarer medium. Can't be the other way around. Rarer to denser is never possible. Why? Ask me why. Rarer to denser, it will be bending towards the normal, so it has no chance of coming back. Look at this. See, if it is rarer to denser, the ray bends towards the normal, so it won't have any chance of coming back. Instead, if it is from denser to rarer, it will bend away, then it is coming back. So the first condition is that the ray should be going from a denser medium to a rarer medium. Second condition is angle of incidence should be greater than critical angle. That is when total internal reflection happens. So when does TIR happen? The ray goes from the question number 1 is this: what are the conditions for TIR to happen? 2-mark question. The ray of light should go from a denser medium to a rarer medium. Number 2, angle of incidence must be greater than the critical angle. Okay, so there are 2 definitions for critical angle. What is critical angle? I told you already. Critical angle is the angle of incidence in a denser medium for which the angle of refraction is 90 degree. Critical angle is the angle of incidence in a denser medium for which the angle of refraction is 90 degree. Or there can be an alternate definition. Critical angle is that angle beyond which total internal reflection would occur. Critical angle is that angle of incidence for which angle? That angle. Which angle? That angle for which the angle of total internal reflection begins to happen. So this is the critical condition, critical angle. So I can just write down Snell's law here. I told you whenever you apply Snell's law, you must write sine by sine here. Then what is equal to n? Angle inside denser medium. This is denser, right? So C should be going on denominator. The other angle is 90. That should be on numerator. So what is the relation connecting these? 1 by sine C is equal to n. 1 by sine C. That is a very important relation. 1 by sine C is equal to n. 1 by sine C is equal to n. This is very, very important. I'm repeating one more time. I'm applying Snell's law at the boundary. Snell's law says what? Sine by sine. You should be writing this way. Sine by sine is equal to n. The angle inside this is denser medium, right? So angle inside denser medium means it is C. That has to come on denominator. And the other angle is 90 which should be going on the numerator. Sine 90 over sine C, which is equal to refractive index. So n is equal to 1 by sine C. And there are a few more points that I'm going to tell you now. Look at this. I'll tell you. This is an extra point which you won't find in textbooks. They might not discuss in school as well, but you will need this. There is a relation called the Cauchys formula. I told you during our regular classes, Cauchys formula, which is that for refractive index, A plus B by lambda square, n is equal to A plus B by lambda square. It actually keeps going, plus C by lambda raised to 4. There are higher terms which are obviously neglected. This is what? This is refractive index of a color, of a light. Okay, n is equal to A plus B by lambda square, where A is what? A and B are Cauchy's constants. A and B are called, these are called Cauchy's constants. Cauchy's constants, okay. But anyway, just know that n and lambda are inversely proportional, as you can see. That's it. That is the only thing you would need. N and lambda are inversely proportional. So I'll write down a few things here. What is lambda's variation? Violet, indigo, blue, green, yellow, orange, red. Right. As you go from violet to red, you know that the wavelength keeps increasing. Violet has the smallest wavelength. Then comes indigo, followed by blue, then green, yellow, then orange. The last one is red. Okay, so if lambda varies this way, n should be varying which way? N and lambda are inversely proportional. So n should have the reverse variation. Violet should be the greatest. Then comes indigo, blue, green, yellow, orange, red. So refractive index of violet color is greatest. Refractive index of red color is smallest. Violet, then indigo, then followed by blue, then green, yellow, orange, and then red. Least refractive index is for red and greatest refractive index is for violet. Okay. And then regarding critical angle, tell me about critical angle. Critical angle and refractive index are again inversely proportional. So it should have the reverse variation. Critical angle for violet is least, then comes indigo, then blue, then green, yellow, orange, red. So who has greatest critical angle? Red has greatest critical angle. Who has smallest critical angle? Violet has. Actually you are not supposed to, you are not expected to learn this by heart, but if you know this equation, everything else is easy. Cauchy's relation is a very important relation. N is equal to, you may have all the time, every alternate year such a question comes. Okay, you check the previous papers to see if I'm lying. Right, n is equal to A plus B by lambda square. This is called Cauchy's formula. A and B are Cauchy's constants. What do you understand from this formula? N is inversely proportional to lambda. Okay, lambda's variation is what? This is something you've been seeing since lower classes, no? Like class 9 or something. Right, lambda, wavelength variation is violet red increasing. Then n variation, n and lambda are inversely proportional. N variation is violet red decreasing. Then critical angle and n are inversely proportional. Again, should be reversed to that of refractive index. So violet red decreasing here, violet red increasing here. So that's all about critical angle there. All right, and you have to know the critical angle for water. Critical angle for water is 47. Critical angle for glass is 42. And critical angle for diamond is 24. You have to learn this by heart. 47, 49, I don't remember. Anyway, I have to check. I'll correct it later. Okay, it's either 47 or 49. I don't remember. Anyway, critical angle for one glass is 42, and that for diamond is 24 degree. Did you understand all these things? Right, take the paper. Let's look at question number 1. All the questions are previous board questions, so all are very important. Question number 1. The refractive index of a certain glass is 1.5 for a light whose wavelength in vacuum is 6000 angstrom. Calculate the wavelength of this light when it passes through glass. So let us write down whatever is given. The refractive index of a certain glass is 1.5. So refractive index is given 1.5. Okay. Then what else? Light of wavelength in vacuum. Light's wavelength in vacuum is given. It is how much? 6000 angstrom. 6000 angstrom. You've been asked to find what? The wavelength in the medium. That must be the question. Let us check it out again. What is the question? Find the wavelength of light when it passes through glass. So wavelength in air is given. Read it again. A refractive index of a certain kind of glass is 1.5. And then what? Whose wavelength is in vacuum is 6000 angstrom. So wavelength is 6000. So you have to find what? Find the wavelength when it passes through glass. It's a direct question since we know the equations now. Lambda air divided by lambda m. This equation you won't find in textbook, but you have to learn this. It's a previous question. So lambda medium is taken to the left side and n goes to the right side. Lambda air over n. What do we get? This is 6000 divided by n is 1.5. That makes it 4000 angstrom. 4000 angstrom. Hope you understood. Anybody has questions on this? Otherwise, you can write this down. Tell me when you're done. Okay, fine. Thank you. Right, let's look at next question. Question number 2. The refractive index of glass is 1.5 and that of water is 1.3. That is given to redirect you. If the speed of light in water is 2.25 into 10 power 8 meter per second. Speed of light is given 2.25 into 10 power 8 meter per second. It's again a previous question. 2.25 10 power 8 meter per second. What is the speed of light in glass? Speed of light in water is given. Speed of light in water is given. Speed of light in glass is asked. It's a direct question, easy to find out. Speed of light in glass. How do you find? N is equal to C by V, right? N is equal to C by V. N is equal to C by V. They are asking you to find out velocity. Velocity is C by N. What is C? Velocity of light in vacuum. 3 into 10 power 8. And they are talking about glass. Glass, it is 1.5. So you cut this and this. You're getting 2 into 10 power 8. Other values are given to confuse you. You won't need those values, okay? They have actually given velocity of light in water, refractive index of water. Those values are given to confuse you. You won't require them at all. Tell me, what is the question again? Read it again. The refractive index of glass is 1.5 and that of water is 1.3. If the speed of light in water is 2.25 into 10 power 8 meter per second, I don't know why it is given. What is the speed of light in glass? Eventually, that is a question. What is speed of light in glass? So speed of light in glass, you can go to the base equation. N is equal to C by V. So what is V there? Velocity in glass. C by refractiveness of glass. C is 3 into 10 power 8. Velocity of light in vacuum, 3 into 10 power 8. By refractive index is 1.5. You cut them out, you get 2 into 10 power 8 meter per second. Did you understand? Question number 3. If the critical angle for total internal reflection from a medium to vacuum is 30 degrees. So critical angle is given. Critical angle is 30 degrees. Find the velocity of light in the medium. Critical angle is given, velocity of light. The only relation involving critical angle is sin C is equal to 1 by n. So I can put it over here. Sin 30 is equal to 1 by n. So n is equal to 1 by sin 30. That is 1 by 1 by 2. That is equal to 2. So n is equal to 2. N is equal to C by V. They are asking you to find V. C divided by n, which is 3 into 10 power 8 divided by 2. That is 1.5 into 10 power 8 meter per second. Repeating, critical angle for total internal reflection is given. Critical angle is how much? 30 degrees. So the moment you see this critical angle term, this equation should come to your mind. This is the only equation you have involving the one which is involving critical angle, right? Sin C is equal to 1 by n. So sin C is 30 there. So sin 30 is equal to 1 by n sin 30. So n goes here, sin 30 goes here. N is equal to 1 by sin 30. That is n 1 by 2. Sin 30 is 1 by 2. So that goes numerator to become 2. So n is equal to 2 there, right? N is equal to C by V. I've been asked to find velocity. I take it to the left side and then n goes to the right side. Velocity is C by n. That is 3 into 10 power 8 by 2. So if you cut this 3 and 2, you get 1.5 into 10 power 8 meter per second. Hope you understood. Any questions? Tell me when you're done. Did you understand? Anybody has questions on this? Okay, fine. Thank you. Like I told you earlier, I'm asking the whole class and very few are responding. Question number 4. Question number 4, 5, 6, then I'll take a short break. Okay. Question number 4. A ray of light propagates from glass 3 by 2 to water 4 by 3. Find the value of critical angle. It's again a very important question. A ray of light propagates from glass to water. Remember, glass to water means both the media are non-air media. So you have to look at relative refractive index. Look at that. A ray of light, underline if you need, a ray of light propagates from glass to water. A ray of light propagates from glass to water. Glass to water. So find the value of critical angle. So I have only one equation for critical angle. Sin C is equal to 1 by n. But while writing n, you have to be careful there. NGW should be written. What is this? Refractive index of glass with respect to water. Why should I write this? Because they say that the ray is going from glass to water, right? Both the media are non-air media. So I need to use relative refractive index. I'm finding it on the margin, NGW. It is actually, I told you, NG by NW. Because N21 is, oh, tell me what? N21 is what? N2 by N1. Relative refractive index is absolute refractive index by absolute refractive index. N21 is N2 by N1. Similarly, NGW is what? NG by NW. Refractive index of glass with respect to water. Why should I see this? Because they have said that it is going from glass to water. The media are non-air media. Refractive index of glass with respect to water is refractive index of glass by refractive index of water. So glass's refractive index is 3 by 2, water is 4 by 3. Take it over to numerator, that makes it 9 by 8. So let's put it over here. Sin C is equal to 1 by 9 by 8. Take the reciprocal. Sin C is equal to 8 by 9. C is equal to sin inverse 8 by 9. If sin C is equal to 8 by 9, C is equal to sin inverse 8 by 9. Did you understand? Tell me when you finish writing this. All right. Okay, thank you. Right. All right. So that's again an important question. It's the previous one. Next one is also very important. A ray of light. It's a little difficult. A ray of light is incident at an angle. It's a previous JEE question as well. A ray of light is incident at an angle I from denser to rarer medium. So a ray of light is incident at an angle I from denser to rarer medium. So I draw the normal here, denser to rarer. So it is going like this. It is coming in at an angle I. Denser to rarer medium. So this is a denser medium. This is rarer medium. The ray is bending away from the normal, Okay, right. The reflected and refracted rays are mutually perpendicular. So there is a reflected component here, reflected component here. Reflected and refracted are mutually perpendicular. These are mutually perpendicular. So obviously Brewster's law is valid, but that is not there in syllabus. Okay. Anyway, the incident ray, this is the reflected ray because there will be partial reflection and partial refraction, right? If you look at a glass, window glass, see, you can see your face on the window glass, right? Even though vaguely, you can see your face on the window glass. That means there is partial reflection. What about refraction? You can see someone on the other side of glass. That means there is refraction as well. So there is partial reflection as well as refraction when you look at transparent surfaces. Or think about this, you look at water surface, you can see your face on water surface, right? At the same time, you can see the fish underwater. That means there is reflection as well as refraction. You see your face because there is reflection. You see the fish because there is refraction. So there is a reflection component and refraction component. And what do they say in the question? The reflected and refracted rays are mutually perpendicular. They are mutually perpendicular. Okay. The angle of refraction and angle of refraction are respectively R and R dash. Angle of reflection is R, angle of refraction is R dash respectively. What is the question? Show that the critical angle is sine inverse tan I. Critical angle is sine inverse tan I. I'll do this critical angle. What is the equation for sine C? Sine C is equal to 1 by n. Sine C is equal to 1 by n. Just give me a minute. Sine C is equal to 1 by n. I need to have I inside, right? So let me just do this. Sine inverse. Okay, n is equal to what? Sine by sine. So denser medium angle is I. It should go on denominator. The other is R dash. That is sine. R dash is what? R dash is, this is I. This is I. 90 minus I, 90 minus I. 90 minus I divided by sine I, cos I by sine I, cot I. N is equal to cot I. So sine C is equal to 1 by cot I. Sine C is equal to tan I. So C is equal to sine inverse tan I. Okay, I'll do this. See this now? Yeah, I'm repeating this. I haven't done it. Okay, so I'll repeat the illustration. Look at this. I'll repeat the illustration. We have a ray of light that is coming from a denser medium. Look at this. The ray of light is coming from a denser medium and it is getting reflected. A part is getting refracted. There is both reflection and refraction. This is reflection component. This is refraction component. And what am I supposed to prove? I need to prove that critical angle is sine inverse tan of I. So keep one thing in mind. I'll somehow require I there. I there. No, I'll need I there. So keep that in mind. So let us see this. Angle of incidence is given as I. Angle of incidence is I. If that is I, this is also I. R is also I. Why? Because in class 10 we have learned that angle of incidence is equal to angle of reflection. That is I. Correct. Angle of incidence is I. So angle of reflection is also I. That is called law of reflection. If that is I, this angle is what? This angle. 90 minus I. Why? Because this is 90, out of which this is I. So this angle has to be 90 minus I. If that is 90 minus I, this has to be I. Tell me why? Because this is 90. If this is 90 minus I, this has to be I. If this is I, this angle is 90, no? So this must be what then? That must be 90 minus I. Let me repeat one more time. See this. See, it's easy. Right. It's a typical one. This angle is angle of incidence. They say that this is R, small letter R. But by the law of reflection, angle of incidence and angle of reflection should be the same. So if this is I, this angle is also I. So if that is I, as you can see, this is 90, no? From 90, this is I, which is gone. So this has to be what? 90 minus I. And if that is 90 minus I, this is 90. They have given that these are perpendicular in the question. Reflected component and refracted component are perpendicular. That's what they say in the question. So this is 90 means 90 minus I is gone. This has to be I then. If that is I, think about this. This is already 90, no? So if that is I, this has to be what? 90 minus I. So my point is my R dash is actually 90 minus I. Let us write that. Let us write Snell's law now. Tell me, how do you write Snell's law? I told you to write sine by sine. What is the angle in the denser medium? Denser medium is this. Angle in the denser medium is I. That should be on denominator. What is angle in the rarer medium? R dash. That is 90 minus I. Okay, sine 90 minus I. You learned that in class 10. Sine 90 minus I is cos I by sin I. That is equal to cot I. N is equal to cot I. You got N as cot I. N is equal to cot I. So let us write the critical angle. What is the equation for critical angle? Sin C is equal to 1 by N. Or sin C is equal to 1 by N is cot I. Sin C is equal to 1 by cot is called a tan I. So C is equal to sine inverse of tan I. Sine inverse of tan I. From this part, I can do one more time. What is Snell's law? I can apply Snell's law here. What is Snell's law? I must write sine by sine first. I told you sine by sine. Then I should write the angle in the denser medium on denominator. This is denser medium, denser. This is rarer. Denser medium angle is what? I. That should go on denominator. And rarer medium angle is what? R dash, which is 90 minus I. That should go on numerator. So sine 90 minus I is cos I. Sine 90 minus theta, cos theta, class 10 trigonometry. Sine 90 minus I, cos I, sin I as such. So cos I by sin I, cot I. Cos by sin is cot. So n is equal to cot I. Let's go back to this equation. Sin C is equal to 1 by n. So sin C is equal to 1 by n is cot I. Cot I, 1 by cot. 1 by cot is tan, cofunction of cot, tan. So sin C is equal to tan I. C will be what? This goes to the right side. Sin inverse tan I. Did you understand now? Question number 6 is also very important. Read the question. A transparent solid cylindrical rod. Transparent cylindrical solid rod has a refractive index of 2 by root 3. It is surrounded by air. A light ray is incident at the midpoint of one end of the rod as shown in the figure. Okay, so let us draw the figure. This is the cylindrical rod. Okay, this is the axis passing through the middle, and then a ray of light is coming in at an angle of theta. And what do they say about the question? I mean, the figure. Prove that the incident angle theta, for which the light ray grazes along the wall of the rod, is sine inverse 1 by root 3. What do we require? What do we require? It is in fact given in the figure. Prove that the incident angle theta. I need to prove that this theta is something. What? Theta for which the light ray grazes along the wall. That means here it undergoes one refraction. Right here, it has to graze along the wall. It has to graze along the wall like this. Graze along the wall. Okay. It means this angle is 90. This angle is critical angle. What is given? I'm repeating. What is the condition they are putting here? I want prove that the incident angle theta for which the light ray grazes along the wall. Underline that part. The light ray grazes along the wall. That means the light ray is sliding over the wall. Grazes along the wall. So grazes means what? You're talking about total internal reflection. So this angle must be 90. If it is grazing the surface, it is 90. That means this angle must be what? Critical angle. So let us find critical angle in the first place. Sin C is equal to 1 by n. Refractive index is given? Yes, 2 by root 3. So sin C is equal to 1 by 2 by root 3. So taking reciprocal, you get root 3 by 2. Sin C is equal to root 3 by 2 would imply that C is equal to 60 degrees. So critical angle I got, it is 60 degree. So since refractive index is given, it's easy to find out critical angle. I use my relation sin C is equal to 1 by n. Sin C is equal to 1 by 2 over root 3. Root 3 goes numerator, root 3 by 2. Sin C is equal to root 3 by 2 means C is equal to 60 degrees. So my critical angle is 60 degree. Critical angle is equal to 60. Okay. I make a little triangle here so that this is 90. So 90 plus 60, I'll write it a little bigger, right? this is 60, and that is 90, and 60 plus 90 is 150, which would make this angle 30. Why? Because inside a triangle, sum of angles must be 180. Look at this. This angle, critical angle, you got this critical angle as 60 degree. Critical angle I have calculated here, it is 60 degree. And this angle is already 90. 60 plus 90 is 150. Inside a triangle, sum of angles must be 180. So this is 90, this is 60. That would make it 150. Then this angle can be 30. Now I can apply Snell's law here on the surface. Tell me what is Snell's law? N is equal to sine by sine. N is equal to sine by sine. What is the angle inside denser medium? Denser medium, this is denser medium. Glass, no? Glass is denser medium. This is air. So what is angle inside denser medium? It is 30 degree. That should come on denominator. What is angle inside rarer medium? Theta. So cross multiply sine theta is equal to n into sine 30. N is what? N is there. N is 2 by root 3. N is given in the question 2 by root 3. Sine 30 is 1 by 2. 2 and 2 are cut. Sine theta is 1 by root 3. Or theta will be sine inverse 1 by root 3. This is exactly the thing to be proved. Show that the angle of incidence is sine inverse 1 by root 3. Did you understand? I'm asking everyone. So moving on to the next question. Question number 7. Question number 7. White light is incident on the interface of glass and air as shown in the figure. It's a previous question again. If green light is just totally internally reflected, which all colors will the emerging ray contain? Okay, so let us draw the figure. Air. So this is air. Okay, air. And the second medium is glass. Glass, and the ray of light is coming from here. It is white light, composite light. There are 7 colors: violet, indigo, blue, green, yellow, orange, red. And they say that green is just totally internally reflected. This is green. Okay. This question can be done in different ways, but I'll tell you the easiest method. Okay. Look at this. Read it again. White light is incident on the interface of glass and air as shown in the figure. So white light is coming here. This is actually white light. White light means it consists of 7 colors: violet, indigo, blue, green, yellow, orange, red. Okay. And I'll tell you the easiest method here. The ray was expected to go along this line, but instead it deviated. Because of what? Because of the medium change. The ray actually was supposed to go along this path, but because of the medium change, the ray underwent a deviation, right? And that deviation is actually given by n minus 1 into a. This is something you learn later on. For the moment, you can take it by heart. Delta deviation is n minus 1 into a. I'll prove it later. We have done this in class. Deviation suffered by a ray is n minus 1 into a. What was the variation of n? Do you remember? Violet had greatest, then indigo, then blue, green, yellow, orange, red. So n's variation. Violet has greatest refractive index, then comes indigo, then blue, green, yellow, followed by orange, and then red. Okay, so violet to red, refractive index is decreasing. We have written this already. Because wavelength increases as you go from violet to red, and refractive index must then decrease as you go from violet to red. Okay, then what do you think about delta? Delta, look at that. Delta and n are directly proportional. So whatever variation n has, delta also should be having same kind of variation. Violet, indigo, blue, green, yellow, orange, red. Violet has the greatest deviation, then indigo, then blue, green, yellow, orange, and red. Repeating this one more time. Refractive index variation we learned already, right? Wavelength variation is what? Wavelength variation is violet to red increasing. Violet, indigo, blue, green, yellow, orange, red. Violet has least wavelength and red has greatest wavelength. You learned this many times. Violet, lambda variation. And n variation should be reversed to that of lambda's variation, because lambda and n are inversely proportional. Cauchy's relation. Okay, so refractive index is greatest for violet and refractiveness is least for red. And we have an equation coming up. Delta, we will derive this relation. We have proved this in class. Delta deviation suffered by a ray is n minus 1 into a. As you can see, delta and n are directly proportional. So n's variation, delta's variation should be identical to that of n's variation. Okay, identical to the variation of identical to the variation of n. So delta's variation and n's variation should be the same. So who has greatest deviation? Violet is the most deviated. Who is the least deviated? Red is the least deviated. So violet is the most deviated. So this is the actual path. Violet is the most deviated. So violet should go at the bottom. This is violet. Okay, violet is the most deviated one. Then indigo. Then blue. Then green is already there. Green is already there. Then beyond that, it should be what? Yellow, orange, and red. Yellow, orange, red. Green is already given in the question. Green just undergoes TIR. So as you can see, this is violet. See, who has greatest deviation? Violet has greatest deviation. So the ray desperately wanted to go along this path, but the violet color suffered. The violet color suffered maximum deviation. So violet is the most deviated. As you can see, violet's deviation is greatest. Okay. Violet gets deviated through this angle. Indigo little less. Blue again less. Then green is already there. Then beyond green, this should be yellow, this should be orange, and this should be red. Because they must come in order, no? In the order of colors, right? And these three colors are an emerging light. They are asking about emerging color. Emerging means the one which is coming out. Emerging light. These three colors belong to emerging light. And these are in refracted light. This one, violet, indigo. They ask in a question, if they ask what are the colors included in the refracted ray, you must say like violet, indigo, blue, and green also, because green has just undergone TIR. Emerging light contains what? ROY, red, orange, yellow. Understood? They might even give you blue here for this question. Then green, yellow, orange, red will be there in emerging colors. Whichever color they give you here, no? In this question, they have given green just undergoing total line reflection. They might even give you blue undergoing total line reflection or indigo undergoing total line reflection. Understood? So from question to question, it can vary. So anyway, here in this question, they say that green just suffers total internal reflection. So beyond green, what all are there? Yellow is there, orange is there, red is there. So those are the colors which undergo refraction, or those are the colors which are included in emerging light. Did you understand? It's a very important question. So if this question comes, you have to draw the figure, you have to write all these things and then explain in your own words. So before moving to the next one, I'll tell you a particular, I'll give you the theory. You know, this is an important point. We have done this in class, right? We have a glass slab. This is a glass slab. And you keep a light bulb over here in the middle, okay? So a glass slab is there and you're keeping a light bulb in it. And then what? A ray of light is hitting the surface and it is grazing the surface. If it grazes the surface, this angle must be what? Critical angle. Correct. See, I have a light bulb here and the light is emerging from this bulb. It is passing through the glass slab, and if it is grazing the surface, this angle must be critical angle. Same thing happens here as well, right? So the ray is grazing the surface, so this angle has to be critical angle. I can bisect this. If that angle is critical angle, this angle is also critical angle. Why? Because this line and this line are parallel and this one cuts both. These are alternate angles, right? Repeating one more time, we have a light bulb at the bottom of a glass slab, and then a ray of light is hitting at an angle called critical angle. So the ray suffers what? The ray just undergoes TIR, or ray simply grazes over the surface. Here also the ray grazes on the surface or simply slides over the surface. So this angle is critical angle. This angle is critical angle. So if I bisect this angle is critical angle, this angle is also critical angle. Why? Because these are alternate angles. And you know, if I take a three-dimensional picture, if I extend this to three-dimensional system, look at this. I have a glass slab here. This is the glass slab. Okay, I have a glass slab, and I have a bulb here, the ray falls at critical angle, critical angle, critical angle, critical angle, critical angle, critical angle. In all directions if you choose. Look at this. Here, critical angle. Here, critical angle, critical angle, critical angle, critical angle, critical angle. So it actually gives you a circle on the surface. If you take the three-dimensional picture, it looks like a cone. It looks like a cone, right? It looks like a cone, right? So on top, you got a circular aperture. Okay. Whose radius is r? This radius is small letter r. And this depth is d. The depth is d. The depth is d, right? So I'll illustrate one more time. We have a light bulb at the bottom, then light ray is falling at critical angle. And then what? On the side also, light ray is falling at critical angle, as you can see. So this is critical angle means, this critical angle means this one is critical angle. Similar way, this is critical angle means this one is also critical angle. They are alternate angles. And then the depth of the slab is small letter d, radius is r. As you can see, it is circular aperture on the surface. Why circular? Because you take three-dimensional picture here. One line, one line, one line, one line, one line. If I take three-dimensional picture, I'll have a cone of light emerging. So my point is, light comes out as a cone. Light comes out through a cone. Okay, or on top, you will see a circular patch of light. Circular patch of light. The question is, what is the radius of that circular patch? So if you keep a bulb there, you can try this at home. If you keep a bulb underneath, you can see a circle. Light will be coming out through a circular area on top, circular aperture. What is the area of the circle? I'll tell you, I'll do this. What is sin C? Sin C is 1 by n. But what is also sin C? Sin C from the figure is opposite side, r divided by hypotenuse. Hypotenuse is root of r square plus d square. Just see this. I'm repeating. This is this is altitude. This is base. So hypotenuse must be root of altitude square plus base square, r square plus d square. So I'm taking sin C in two different equations. Sin C's original equation is 1 by n. Sin C can also be written as opposite side r by hypotenuse. Hypotenuse is root of r square plus d square. Root of r square plus d square. Okay. And then I can equate these two. These equations are what? Left sides look the same. So I can go to the right side. I can equate them. 1 by n is equal to r divided by root of r square plus d square. Cross multiply. I'll write it here. nr is equal to root of r square plus d square. Square it up. You get n square r square. N square r square is equal to r square plus d square. My aim is to get r, so I'll get r's on one side. This is n square r square minus r square is equal to d square. So r square is taken common. R square into n square minus 1 is equal to d square. I've taken r square common here. Tell me what r square is now? D square over n square minus 1. What I need is r, so r will be square root d by root of n square minus 1. There can be two types of questions. One, they might ask you to derive this. It's a textbook question, chapter and exercise question. They might ask you to derive this equation, derive the expression for radius, or they might ask us in a numerical. So you have to learn this equation by heart. They'll give you depth at which bulb is located, then refractive index, then they'll be asking you to find the radius and probably area. Area is pi r square. Okay, and like I told you, they can ask us in a derivation. This can be asked as a derivation. Derive the expression for radius of the circular patch through which light comes out. R is d by root of n square minus 1. Or they'll give it in a numerical. They'll give this d value, n value. They'll ask you to find out radius and area. Area is pi r square, circular area, right? And same question can be asked in another way. You know, just imagine in place of bulb. Okay, I'll draw but fresh figure, right? I have the same thing, no? I have, this is water, okay? This is water. And then there is a fish here, fish. What is the area through which fish underwater sees the outside world? Fish underwater sees the outside world. Okay. It sees the outside world means light is again coming through this cone. Because light has what? Reversibility. If light goes out through this cone, light can come in through this cone only. Light can come in through this cone only. Light is actually going out through this cone. Here, 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 here. Light can go out through this cone only. If a ray of light falls at a greater angle, it will come back. It will undergo TR. That's again a previous board question. To draw the ray of light, to trace the line, if the ray of light falls at a greater angle. What if it is falling at a greater angle than critical angle? If it falls at an angle which is greater than critical angle, it will come back. It won't come out. So the rays are always coming out through this cone. Similar way, rays are coming in through this cone, which means light rays coming in, light rays coming in, light rays coming in, light rays coming. A fish can see the outside world when light from outside world falls on its eyes. When do you see something? How can you see the pen? How can I see the pen? Light falling on the pen gets reflected and that falls on my eye. That is when I see it, right? That is the perception of vision, right? That is when I see it. So similar way, if the fish or you underwater is to see the outside world, tell me what? The ray must come to its eyes. The ray must come to the fish size, right? So my point is, again, the radius will be d by root of n square minus 1. So be it this bulb case, you know, if you keep a bulb underneath, what is the area through which light is coming out? You have r is equal to d by root of n square minus 1 and area is pi r square. Second question is, a fish or a man underwater sees the outside world through a circular aperture. What is radius? What is area? Again, r is equal to d by root of n square minus 1. Area is equal to pi r square. Did you understand? If yes, write this down. Question number 8 and question number 9 are previous questions. Both are based on this concept. Let us do. Question number 8. A bulb is located at the bottom of a pool of liquid of refractive index n and depth h. The object emits rays upwards in all directions. A bulb is located at the bottom of a pool. A bulb is located at the bottom of a pool of refractive index n and depth h. Depth is h. In place of d, they have used h here. The object emits rays upwards in all directions. Okay. So that a circle of light is formed at the surface of the liquid. Circle of light is formed at the surface. By the rays which are refracted into the air. What happens to the rays beyond the circle? Determine the radius and area of the circle. What happens? It's an important one. I told you, no? Previous question. What happens to rays beyond the circle? Tell me, beyond the circle, the ray gets reflected. So you should write the answer this way. Beyond the circle, beyond the circle, beyond the circle. See, beyond the circle, if a ray comes in, what happens? It's falling at a greater angle. Angle of incidence is greater than critical angle. Tell me what? In such a case, the ray undergoes refraction instead of, reflection instead of refraction. The ray would come back instead of going out. Okay. So you should write the answer this way. What happens to the rays beyond the circle? Beyond. So for the rays beyond the circle, there will be total internal reflection. There will be total internal reflection. There will be total internal reflection. Okay. Determine the radius and area of the circle. I am not doing it. Determine, it's a 3-mark question. Determine the radius means you have to do this derivation. R is equal to d by root of n square minus 1. They have used h here. So R is h. Area is pi r squared. So pi into h square by n square minus 1. Just write this. But you know, they are asking you to determine. Determine means you have to derive. Did you understand? You have to derive this. I won't be deriving it again because we have done it now. Done it just now. So R is h by root of n square minus 1 and area is pi r square. That is pi into r square. Square of this is h square. Root is gone, n square minus 1. Did you understand? Okay. Moving on to the next one. So I'm leaving the derivation to you. You can derive at home. Okay. But you have to do that. Question number 9. A small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeter. So depth is given. Depth is 80 centimeters. So 0.8 meter. Right. 80 centimeters. What is the area of the surface of water through which light from the bulb can emerge out? What is the area? Read it again. Question number 9. A small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeters. So water has a depth of 80 centimeters, so 0.8 meter. What is the area of the surface of water? Area is circular area through which light from the bulb can emerge out. Refractive index is given. Area, let us write down the equation, pi r square. Area is pi r square, that is pi d square by n square minus 1. Let us put it. So pi into d square, 0.8 square divided by n square minus 1. It is water, right? Yes, n square minus 1. Water means 4 by 3. The whole square minus 1. 4 by 3. Water is 1.33, which is 4 by 3, which is pi into 0.64. 8 square is 64. So 0.8 square is 0.64. Divided by 4 by 3 square, 16 by 9. 16 by 4 square, 16. 3 square, 9 minus 1. So pi into 0.64 divided by 9 comes here. 16 minus 9 is 7 by 9. This goes numerator. So 9 by 7 into 0.64 pi. I can cut roughly if you want. If I want, 7 and 7 nines are 63. So 0.09. 64 is approximated as 63. 63 and 7. 63 and 7. 9 sevens are 63. 9 to 7 is 2 places, 0.09. So 9 nines are 81. So 0.81 pi meter square will be the area. 0.81 pi meter square. Did you understand? Question number 12. Actually, that belongs to another section that actually comes from spherical surface. So that will come in another paper. Don't worry, I won't be doing it here. It's a previous question again. It's a reader question as well. Question number 12. So I'll be doing that in another paper. 13 is a homework for you. I'm leaving 13 as it's a very, very easy question. 13th question, I'm leaving it as a homework for you. So we have 2 more questions remaining. Question number 10 and question number 11. We will do them and wind up for the day. Right. Question number 10. A transparent cube of side 210 millimeter. A transparent cube of side 210 millimeters. Look at this. A transparent cube of side 210 millimeters. Side is 210 millimeters. Okay. Contains a small air bubble. It contains a small air bubble somewhere here. I don't know where it is. Small air bubble. When viewed through one face of the cube, its apparent distance is 100 millimeter. So when viewed through one face, its apparent length is 100 millimeters. When viewed through the other side, the apparent length is only 40 centimeters. See, this is 40 centimeters. 40. So I'm repeating. Read the question one more time. Read the question. So there are through 2 faces now. Total distance is what? Total distance is 210 millimeters. Read it again. A transparent cube of side 210 millimeters. A cube, transparent cube, 210 millimeters contains a small air bubble. There is an air bubble inside. I don't know where it is. Its apparent distance when viewed through one face of the cube is 100 millimeter. So when I view from this side, its apparent distance is 100 millimeter. When I go over to the other side and when I view from this side, the apparent distance is 40 millimeters. See this? When viewed from the opposite face, it is 40 millimeters. What is the actual distance of the bubble from the second face and what is the refractive index? So actual distance, I am taking the actual distance as x from the first surface, okay? So from the second surface, actual distance is what? 210 minus x. Actual distance from the first surface, I have taken it as x. So from the second surface, it is 210 minus x. So I can write the refractive index equation. Refractive index is what? Real depth by apparent depth, if you remember. Refractive index was written as real depth divided by ratio of real depth to apparent depth. So n is equal to real depth from the first surface. No, from the first surface. What is real depth from the first surface? Real depth from the first surface, when I see the real depth, I have assumed it to be x. And apparent depth is what? 100. You can keep it in millimeter, no issues. Equation number 1. When I view from the other surface, real depth is what? 210 minus x, right? Real depth is 210 minus x. So there again it is n. 210 minus x, real depth, by. Apparent depth there is 40. Equation number 2. But both the refractive indexes are the same. Why? If you look from this side and look from the other side, material remains the same. It is glass, right? Same refractive index. So I can equate them. X over 100 is equal to 210 minus x over 40. So let us simplify. 0, 0 cut. Then cross multiply. 4 into x, 4x. 210 into 10, 2100 minus 10x. So this goes to the left side. It becomes plus 10x. 10x plus 4x. 14x is equal to 2100. X will be 2100 divided by 14. That is 150 millimeters. Remember, they have asked you to find the real actual distance from the second surface, second face. So, actual distance from second face. Actual distance from second face. Second face is what? Actual distance from second face actually not x, it is 210 minus x. 210 minus x. It is 210 minus x is 150. X is 150, 210 minus x. That is equal to 60 mm. Also, you've been asked to find the refractive index. It's easy to find out. You can use either of these equations. N is equal to x by 100. Look at this x by 100 or this one. So, x is 150 by 100. 0, 0 cut. That will give you 1.5. The refractive index is 1.5. It's a 3-mark question. Did you understand? Repeating one more time. When you look from the side, the real depth is, I have taken as x. Apparent depth is 100 millimeters. From the other side, real depth is 210 minus x. Because the total distance is 210, this is x means this must be 210 minus x. Apparent depth from the other side is 40. And then I write down two equations. N is real depth by apparent depth. Real depth is x, apparent depth is 100, x by 100. From the other side, real depth is 210 minus x, apparent depth is 40. So equate them, solve it, you get 150 millimeters. But this is x from the first surface. Distance to the bubble from the first surface. But instead, they have asked for distance from the second surface. So actually, I need to find out 210 minus x. 210 minus x is what? 210 minus 150, x is 150. That is 60 mm. And again, second question is to find out refractive index, for which I can use this equation, x by 100. It is 150 by 100, that makes it 1.5. Okay, let's move to the last question of the day. Read the next question. That's again an important one. All these are previous questions, okay? Right. A mark is made on the bottom of a beaker and a microscope is focused on it. A mark is made on the bottom of a beaker. This is bottom of beaker, right? Bottom of beaker, and a microscope is focused on it. Microscope, this is your eye. You are looking from above, okay? This is a beaker and an ink mark is, a mark is placed on, a mark is made on the bottom of a beaker and a microscope is focused on it. The microscope is raised through 1.5 centimeters. You are raising the microscope through a distance of 1.5. Look at that. Microscope is raised through a distance of 1.5 centimeters. Okay. Microscope is raised through 1.5 centimeters. To what height water must be poured into the beaker to bring the mark again into focus? So to what height you must pour water? Okay, so you are just pouring water till this point. Just assume. Okay. Tell me, shifting the, this is actually shifting the position. You are shifting the microscope up means you have to shift the image, right? So shifting the position, do you remember? T into 1 minus 1 by n. Shifting the position, they are saying it is 1.5. I'll keep it in centimeter. T into 1 minus 1 by, is it water? Yes, 4 by 3. So what 0.5 is equal to T into 3 goes numerator, 1 minus 3 by 4. So 1.5 is equal to T into 1 minus 3 by 4 is 1 by 4. Let it go to left side. T is equal to 6 centimeter. T is actually thickness of the slab. In this case, it is actually what? The thickness or the height up to which water must be filled. I'm repeating the question one more time. A mark is made on the bottom of a beaker and a microscope is focused on it. And then what? The microscope is raised through 1.5. So you are looking at the ink mark, you are raising the microscope through 1.5 meters. That means same shift should be there in the case of image also. For that, you have to fill it with the water or glass or something else, transparent medium. Here they say to what height water must be poured. So you're pouring water into this so that the image also shifts up. Then what are they asking? To what height water must be poured? So height of water into the beaker so as to bring the ink mark again into focus. So if the ink mark is to come into focus again, it should have the same shift as the microscope. So x is shift is given by what? I have given this equation already. Thickness into 1 minus 1 by n. X is shift 1.5. I'll keep it in centimeters. I'll get the answer also in centimeters. T into 1 minus 1 by, you're pouring water. Even if it is not given, you have learned this 4 by 3. 3 goes numerator, 1 minus 3 by 4. So that makes it 1.5 is equal to T into 1 by 4. 4 goes there, T is equal to 6 centimeters. That means 6 centimeters is the thickness of water. So they are actually asking the same thing. To what height water must be poured? They are asking you to find this height. Okay. Question number 12. Like I said, it actually is from a spherical surface portion. So it will come in another paper. Don't worry. It's a previous question again. It's a reader question as well. Then question number 12 is a homework. Sorry, 13 is a homework. It's a very easy one. You have to do that. If you don't get the answer, you get back to me. Okay. So I'm winding up the session for the day.